All right, welcome back. I hope you're having an awesome time so far. Our next speaker is Lukasz Kidzinski. He is a researcher at Stanford University. Please join me in welcoming him to our virtual stage.
Hello, everyone. Thank you very much for the introduction. And let me share the slides very quick here. Okay, so today I'll talk about measuring human movement and measuring disease progression using single cameras videos and AI. So let me start right away with asking the main question: why do we analyze movement in the first place? There are three main populations that we might be interested in and that we are interested in at Stanford. And first population is the population of elderly subjects who struggle with diseases like Parkinson's disease, Alzheimer's disease. And in that case, for choosing the best treatment for those patients, what normally happens is that we try to get some quantitative assessment of how they move. And based on that, we infer at what stage their neurological disorder is, and then we choose treatment based on this data. Similarly, for pediatric population, there are diseases like cerebral palsy that again limit social participation of children, and then by limiting the social participation, they lead to even more severe problems with their musculoskeletal system. So again, we would like to, and we normally try to quantify their movement and other abilities, and then choose treatments based on that. Finally, there's the third population of people who rely on assistive devices in their everyday life. Those could be prosthetics or more recently, exoskeletons. And whenever we want to choose parameters of those devices or just choose the prosthetic that is perfect for a given patient, we need to quantify their movement first and then take decisions. In our recent work at Stanford, we're particularly interested in cerebral palsy population. So here you can see one subject, a patient who comes to the clinic. What usually happens is that a doctor asks the subject to walk across the room. And already from just looking at the subject, they can figure out that they land on their toes, they have some asymmetric gait, there are some muscular problems with abnormalities in their bone growth, and all these are symptoms of cerebral palsy in this case. But the main information here is that the doctor can already, from just looking at a patient for a couple of minutes, then they can figure out what is happening there. Now, that's just a qualitative assessment. What happens next, usually with subjects like this, is that they are asked to go to a so-called Gait laboratory, where a physical therapist puts markers on the lower limbs of the subjects. You can see those small little white dots. And again, they're asked to walk across the room, but now this room is filled with cameras all over. And just as you can see here, those cameras are collecting signals. They're measuring positions of those markers in 3D. Well, they measure in 2D, but then we reconstruct that to 3D. So the raw data looks more or less like this. That's what kind of data is collected. The cameras altogether see those clouds of points traveling in the space. And now, since you have multiple of those markers on every part of every limb, you can measure joint angles in the subjects. And that's the data that the doctor will be actually already familiar with. If you cannot bend your knee fully, then that's one of the symptoms of cerebral palsy. So now, just to sum up how the current workflow in clinics work, let's look at this slide. So here we see that first, we collect data, as I showed you previously. We collect data in the lab with markers on the body of the subject. Then those trajectories are corrected manually or semi-manually by some experts working, collecting the data, some engineers working with the motion capture system. The physical therapist is collecting measurements of the body. All this goes into a so-called inverse kinematics model, where based on changes of positions of markers and the anthropomorphic measurements, we are able to read joint angles. Now, in order to make those measurements comparable across subjects, what usually happens is that we take landmarks corresponding to the time when the subject hits the ground with their toes. So with those landmarks, we can segment the time series into pieces which are comparable between subjects. Then this data goes to the expert. Expert analyzes the data, runs some scripts on that, and generates a report. So that's a beautiful and well-established pipeline. And this gives a relatively high fidelity of data that works perfectly in the hospital, but there are multiple disadvantages of measuring human movement this way. So first, it takes around 30 minutes to set up the system. So putting the markers on the body of the subject just takes time, and this needs to be done precisely. So that's cumbersome for physical therapists normally, especially if you work with children. That takes even longer. Equipment is expensive. So those cameras that I showed you that are there in the hospital costs like $100,000 or more. You need trained personnel to actually place those markers in the right positions, and engineers to collect the data, to work with the with the computer system that coordinates everything. You need the person to visit a clinic, and that's a big constraint. And since we have only a couple of clinics equipped with this sophisticated hardware, some people just physically don't have access to that. You need space in the hospital. That space can be used for other more economically viable activities at the hospital. Usually that's this motion capture part is not generating much income. So even from economical perspective, that's not something that hospitals want to carry. There are some scheduling issues. It's not, you cannot have multiple subjects at the same time. And it's just time consuming. So the entire process, even the engineering process after the collecting data, that takes time. So your throughput at the hospital is quite low, and you cannot have subjects visit the clinic multiple times because that's just not feasible. So what we were wondering is, how can we fix that? How can we collect more data for taking clinical decisions or for evaluating clinical decisions, clinical treatments? And one of the ideas for that comes from recent advancements in AI and deep learning. In particular, since we know, as I showed you in the first video, since we know that in the video itself, there's a lot of information that the doctor can actually use for their diagnostics and treatment decisions, maybe we can simply use single camera videos for getting relevant information. Maybe not as good as with motion capture, but already good enough for screening patients at home, or for checking whether a subject's progression of the disease changes over time, for example, after treatment. Like one of the pain points on the clinical side right now is that when a doctor performs some treatment, surgery, or even physical therapy, they cannot measure progress because access to the Gait laboratory is limited. So they don't have a quantitative metric whether a subject is getting better or they are getting worse and they should go back to the hospital. And that's a really difficult thing, both for doctors for coming up with new treatments and for patients who are just not getting access to the best care they could. And finally, we would like one scenario that we are envisioning is that we could use the system for screening subjects at home. So you can imagine a scenario where a mom pulls out a phone from her pocket, just clicks on an app, records the child, presses a button, and figures out whether this child has really some symptoms of cerebral palsy and should quickly go to the hospital, or that's less severe and maybe they should just reevaluate that in a month or so. So there are some screening possibilities here. So we want to investigate whether that's actually possible with the current technology. And the approach that we are suggesting is based on recent advancements in computer vision and in deep learning and AI, and we'll be using two different deep neural networks to achieve what we want to get those metrics sort of at home. And that's recently published in Nature Communications. So you can see more details about the method that I'll be describing today in the paper that is linked here. So the procedure that we are proposing is a two-step procedure. So first, you collect the data with a mobile phone. You just record your daughter with a mobile phone, and then we run an algorithm, a computer vision algorithm called OpenPose, for another algorithm for key point detection. And what this class of algorithms do is that it finds key points on the body of the subject, or some landmarks. In this case, some shoulders, elbows, hips, and so on. So you get virtual markers. I showed you previously that we were putting markers. A physical therapist was putting those white reflective markers. What's happening here instead is that we don't have any markers, and still the computer vision algorithm can figure out where those anatomical points are. And then if we have this data from the algorithm, we can try to generate a report for a doctor based on that. But what we try to do that, like we try to look at joint angles in this 2D output, but it turned out that it's very noisy. The output is very noisy, like subjects are walking, not that, like the environment is not that controlled usually. So what we decided to do is to introduce the second step in our procedure, where we run a neural network for denoising the data from the OpenPose algorithm. So we are generating a report based on trajectories from OpenPose, but we use a neural network to actually project these trajectories into a report. And I will show you some details now. Just one quick note on the first step of the procedure. So I was mentioning OpenPose. There are multiple other algorithms for key point detection. And the reason why in recent years we saw that many new algorithms coming out is that first, deep learning became a commodity. Like we can now very easily train those algorithms. And but for those algorithms, we need large data sets. And organizations called COCO, mainly supported by Microsoft, produced this large data set of 200,000 images with 250,000 people annotated in images, and around 1.7 million key points annotated in those subjects, in those images. So by using standard machine learning and standard deep learning techniques, and with this large data set, we can have an algorithm that finds those key points in the new images. So we can automate this task easily with deep learning. So this we're taking for granted. We are using the OpenPose algorithm that for the video that I showed you at the beginning, which looks like this. So you can see already that it's quite accurate. There is some noise. It finds some people in the background and so on. It mixes up the left with right occasionally, but overall it's a very accurate output. And if we manage to denoise it a little bit, we hope that it's actually going to be clinically relevant, as I will show you in a second. Here's another video with a subject that is more severely affected by cerebral palsy, and still we see that the output from OpenPose is reasonable. So with that, like seeing that those results are encouraging, we got access to a data set from Gillette Children's Hospital from our main collaborator on that paper. And there, for the last 30 years, they've been collecting videos of subjects in the clinic. So we got around 1,800 videos of over 1,000 subjects. And for all of those videos, for each one of those videos, we had a corresponding motion capture trial. So we knew the ground truth observations. So now the only question is how to map videos to this motion capture trial. So how from the video we can predict measurements that they were getting from this classical pipeline that I was showing you earlier. And for that, we again use a neural network. So first, we run this first step of the procedure. On all videos, we run OpenPose algorithm. So for all videos, we get measurements, as you can see here, where we have frame and position of the joint or of a landmark over time. It generates a few, like 2 dozens of time series. We put that into a neural network to get variables that we are interested in. So those variables were derived from motion capture trials. These trajectories were derived from videos. So the only missing part in the equation is actually the actual neural network, but then the advancements in deep learning allow us to train an algorithm that finds a mapping from those trajectories to these end variables that we know for our videos. And now whenever we have a new video, we just run it through the pipeline. Since we already know the neural network, we run OpenPose on it, we get the trajectories, we have our trained neural network, and then we can predict the variables for a new video. So how does that perform in practice? We checked whether we're outperforming this very naive algorithm of taking the open pose output and trying to calculate some joint angles. So one of the variables that we're interested in is the peak knee flexion. So children with cerebral palsy are not able to completely flex their knee. So we would like to predict this parameter. If we just look on the open pose output and we just measure the knee angle and look for the peak, we get the correlation with the true values at 0.51, correlation with values from the motion capture. If we run our machine learning, deep learning based procedure, we get correlation of 0.83. So there's quite a big boost thanks to the fact that the neural network can actually denoise some of the information. Similarly, for other metrics that we're interested in, like the Gait deviation index, we managed to predict it with 0.75, which we've learned from literature that can be already clinically relevant. Of course, that has to be validated in a clinical trial, but it is already indicating that these technologies can be useful in practice. Now, one big question that people have when they see those neural networks-based approaches is whether it's a complete black box and we cannot really learn anything about what is happening there, and we can just use them as is. And that's not necessarily the case. Of course, the actual neural network has millions of weights that we cannot interpret easily, but we can still query the neural network to see what is working well or what is not working well. So in our analysis, we're working with sagittal plane. So we're looking only on the side view of the subject. One question that we had is whether if we added the frontal plane, so if we added images like this and information from those images, would we be able to improve the results of our predictive models? And it turned out that yes. So in this case, we were looking at the error of the GDI prediction. So we have our prediction from our model. There is some true value. Those two mismatch. And we check whether this mismatch is actually correlated with some information from this plane. And if yes, then it means that if we added this information to our network, we could get better prediction. And in this case, it turned out that yes, we can improve our models if we add the frontal view, and in particular, the ankle, the so-called foot progression angle, which is the angle of the ankle visible only in this plane. And finally, the third question that I mentioned earlier was whether we can predict who will receive a surgery. And again, our model was able to predict something, whether a subject is going to get a surgery or not, better than models based purely on some holistic metrics like the GDI. So again, there's some hope that those video-based models are actually be more useful than the data we already collect. And that's kind of also corresponds to what we learn from talking with doctors. So clinicians say that they believe that in the video itself, they may sometimes see more information than they get from this motion capture trials because of how they perceive the per subject walking. And that's not necessarily visible just only in the clouds of points from motion capture. So let me now summarize where we are with this project and what kind of further research that triggers. And I will show you 2 or 3 slides on what we're doing right now to learn more about potential of those technologies in practice. So the key takeaway from the entire talk and paper and our research is that these technologies, deep learning coupled with computer vision or just computer vision and deep learning can already be used for predicting quantitative gait metrics and for predicting disease progression in at least cerebral palsy, but potentially in other populations. So that's a big result on its own. Clearly, we are a research lab, not a commercial company. So there are a few other steps that have to be taken to actually deployed in practice. But nevertheless, we see that there is a potential, and that if enough investment was given into this direction, we could see some practical uses of this technology. We showed that technology work on cerebral palsy population, but of course, there's nothing that could stop us using it for other populations. So there's as long as we have a data set of similar structure as the one that we got from cerebral palsy and from Children's Hospital, we could use it. We could train our models for that. So now, based on our research, there are two big questions that arise. So first is is whether we can actually use it in practice. So we trained the model on hospital data, but now the question is, can we really take out a mobile phone, record the child, and get some clinically relevant measurements? And the second question is that since we relied on this large data set, it kind of limits the applicability of the method for other populations where you don't have that good data. Like the data that we got was like for research communities, it's quite unusual to get such well-controlled data from a hospital. And so we are investigating how can we build similar models on smaller data sets. And I will show you a few slides on how we actually do that. So for checking whether we can actually collect any data in the wild, we started a new project, which you can find at Sittostand AI. And that's our project at Stanford, where we try to recruit people from all over the world to perform a so-called sit-to-stand activity, where you just basically sit down and stand up 5 times as fast as possible. We correlate that with some self-assessed health metrics. So that will be a way for us to validate whether subjects at home can actually collect some data. And we decided to use a simpler activity than walking, because it's actually quite difficult to record a subject at home to walk across the room, because sometimes it's just hard to find 10 meters for at home, like in small apartments. It's just cumbersome to record such videos. So we decided to use a simpler activity here. And the nice thing about that is that we, in the middle of the pandemic, where you cannot actually go to the laboratory and collect measurements, we were able to already run a preliminary study on multiple subjects just recording themselves at home. So you can imagine that this can scale very nicely compared to classical approaches to biomechanics. And finally, in the context of training our models on smaller data set, one limiting factor for the current approach was that the open pose just gives us 2D reconstruction of the subject in a frame. If we wanted to run existing pipelines, for using smaller data set, we could use existing pipelines that were prepared for motion capture data, where you don't need that much data for actually getting meaningful results, but then you need 3D input. And OpenPose just gives 2D input, but actually from 2D video, you can reconstruct some of the 3D information. And that's what we're trying to do. So here's the video of one subject on the left, and on the right, we see a 3D reconstruction using, again, some computer vision-based algorithms. This can work for healthcare, but of course, there are no limitations. So here's another video where we apply the same algorithm to some old video of a picture. So that's all I wanted to show today. Thank you again for inviting me to give this talk and for staying with me and listening to the talk. I would like to thank my co-authors of the paper that I was describing. So Brian Young was a master's student at Stanford and was the co-first author on the paper. Jen Hicks and Apurva Ragapal are research scientists in the lab that immensely helped on this project. Scott Delp is the PI, and Michael Schwartz was instrumental for giving us data, of course, but also in explaining us what we can actually look for in this data, and on the data science part as well. There are a few funding agencies that helped us, mainly NIH, who supported us through Mobilize and CCSRR grants. Thank you. I'll be happy to take any questions now.
Awesome. Thank you so much, Lukasz. If you could stop sharing your screen, I know the audience wants to give you a huge virtual round of applause. Thank you. All right, for the audience, it's time for you to make your way to your next session. Along the way, make sure you accept your connection request and check out our amazing AI exhibits. Thanks so much, and we'll see you around.